Back again with section 3.4. We're dealing with concavity and the second derivative test. The examples went kind of long in the first part of this video I did, so I'm breaking this up into two parts. First part we talked about concavity, and we talked about how to tell concavity taking the second derivative. In part 2, I'm going to start talking about points of inflection and looking at what the actual second derivative test. Yes, although we used the second derivative, it wasn't the second derivative test. Kind of like the first derivative test came after we used first derivative to find increasing, decreasing. Second derivative test we're going to use even though we've been using the second derivative to test. Yada, da, yada, da. Okay, so let's pick up where we left off. At points of inflection. Now again, when we were doing those, we wanted to see where the concavity changed. Go back. Where the concavity changed, and where the concavity changed is where the second derivative was 0, because we're looking at positive or negative. It's going to change when it can be 0. So a point of inflection is what we're going to call this place where the concavity changes. So we have a little bit an odd one on this definition. Not all books you include this in their definition of point of inflection. But we have a function, we have to be continuous on an open interval, and C is a point in the interval. This says if the graph has a tangent line at the point. That's the kind of an odd thing in there. That not all, we're talking about, can we actually find the derivative at that, can we draw a line, a tangent line at that point when we're looking for a point of inflection? It's a kind of an odd thing with this book. I'm just going to kind of gloss over it, but I include it because it's a text we're using. Yeah, let's go back to this again. The more important thing is the point of inflection. It's a point of inflection if the concavity changes. So we are looking for places. A point of inflection, by definition, is a point where the concavity changes. So, come on. So, we do this again. Point of inflection on the graph is where, and a point of inflection will always have the second derivative is 0 or does not exist. If it is a point of inflection, the second derivative of 0 is 0 or does not exist. It does not mean that if the second derivative of 0, it is a point of inflection. If its second derivative is 0, it may be in a point of inflection, but it's not guaranteed. But if it is a point of inflection, the second derivative will be 0, or the second derivative will not exist. So that's why those are the points, again, like with the first derivative test, those are the points we're going to concentrate on. Oh, it won't let me do it there. Okay. Doesn't like me. So, let's do one of these puppies. Give this a try on your own. It's pretty much like the points we did before, except I want you to first determine the points of inflection and then discuss the concavity. We really did it on the other ones. We just didn't call them points of inflection. Give it a try, then come back to me. This one I gave you a much nicer formula to work with. So we're going to find the first derivative is going to be 4x to the third minus 12. No. Sorry. No, that's right. 4x to the third minus 12x squared. So the second derivative is going to be 4 times 3 is 12x squared minus 2 times 12 is 24x. And I'm going to factor out my common factors because I'm trying to find the second derivative equals 0. So 12x times x minus 2. So I could have my possible points of inflection are going to be where 0 equals 12x times x minus 2. So at x equals 0 and x equals 2. I'm not guaranteed. Usually those will be your points of inflection, but not always. So we do want to check those. So to find out if they're points of inflection, we're going to look at concavity. That's what we were doing before again. We say, break this up. Our interval, we're going from negative infinity to 0, from 0 to 2, and from 2 to infinity. And we're going to, again, do a test point. Let's go -1. -1, and that's pretty easy to calculate on this one, because -1, that's going to be 12 plus 24, 36. That's greater than 0. So if greater than 0, it's going to be concave up. Here I'll check double prime at 1. That's going to give me 12 times a -1. Oh, -12 is less than 0. So this is going to be concave down. We're going to check at 3. So I'm going to get here 36 times 3 minus 2 is 1. Is 36, which is greater than 0. So that's concave up. So here we're changing. So it's a point of inflection. Here we're changing from negative, from going down to up. So that's a point of inflection. To call these points of inflection, we have to see, does the concavity change? So points of inflection are going to be x equals 0. So that's going to be the point 0, 0. And x equals 2. That's going to be the point, when I didn't figure that one out. 2 to the third is 8, so that's 32. 2 squared is 4 minus 48. So -16 are my points of inflection. And my concavity is, it's going to be concave up from negative infinity to 0, concave down from 0 to 2, and concave up from 2 to infinity. That brings us to the second derivative test. So, second derivative test. Bye-bye, mouse. Well, going crazy again. Go back up. Whoops, wrong direction thing. Okay, so for the second derivative test is actually like the first derivative test. Second derivative tests are looking for your relative extrema. So what this is saying is, if we find where the first derivative is 0, that's where our critical points are. That's where we could have our extrema. We plug in the c value into the second derivative. Oh, that should be a c there. another typo here. If the second derivative is positive, that means it's concave up, so that means that must be a relative minimum. If the second derivative is negative, that means it's concave down, so that must mean it's a maximum. So that's going to work a little bit opposite of what you would expect. So I always come back to, when I'm doing the second derivative test, use it to say, hey, what's the concavity at that point? Oh, that has to be a minimum. That has to be a maximum. So that's the way, instead of having to check 2 points on either side of the critical point, we just check the critical point in the second derivative, and it tells us relative minimum, relative maximum, unless it equals 0. If the second derivative equals 0, the test fails. You cannot use the second derivative test. It may be a relative maximum. It may be a relative minimum. It could be neither one of those. But at that point, if you check a critical point on the second derivative and you get the second derivative is a 0, you're going to have to go back to the first derivative test and say, let's look on either side of that point. Is it increasing or is it decreasing? To tell you if it's, concave up or concave down, or neither. To tell it if it's a relative minimum or a relative maximum. So let's try one of those problems. Find the relative extrema of f of x equals negative 3x to the fifth plus 5x to the third. And I want you to try using the second, I want you to do this using the second derivative test. Give it a try, and then I'll walk you through this one. So f of x equals negative 3x to the fifth plus 5x to the third. So our first step is we're going to find, we don't want to do that. First step is we're going to find we have to get to the second derivative. But actually we're going to, we got to start with the first derivative. So 5 times the negative 3, x to the fourth, 3 times 5. Oh, isn't that convenient? Because now I could go straight to the second derivative, but I need my critical points. So I'm going to take a quick break here. I'll say that's negative 15x squared times x squared plus 1. Not plus 1, minus 1. I'm factoring out that negative. So we're going to have a critical values at x equals 0, x equals 1, x equals negative 1. This is important because second derivative test, we're going to check the second derivative at our critical values. So I'll put this over here. Then we'll come back to here and find our second derivative, because we need to check it in our second derivative. I need our second derivative. Find our second derivative, I'm going to come back up to this one, because that's much easier. This is a product rule. No, forget that. 4 times negative 15 is negative 60. X to the third. 2 times 15 is 30. X squared. And I'm not even going to worry about anything else with that, because I'm just looking for my relative extrema. I don't care about what my concavity is, so I don't have to find the inflection points on here. So I'm going to say, now come over here and say, do my second derivative test. What is f double prime at 1? So I plug it in here. Negative 60x, or x, times 1 cubed plus 30 times 1 squared. And that's going to be negative 30. And this is less than 0. Means it's concave down, so this is a relative max. So I know now I have a relative max at x equals 1, and that's the point 1, 2, because I plug in 1 into this equation to get that value. I plug in my negative 1. Negative 60 times negative 1 to the third plus 30 times negative 1 squared. That's going to give me positive and positive. That's 90. So that's greater than 0. Concave up. That's a relative min. X equals negative 1. And it's going to be the point negative 1, negative 2. That makes sense. This is an odd function, so I should have odd symmetry. So the opposite x should give me the opposite f of x. That looks good. If I plug in f of 0, I get 0. We cannot determine with second derivative test. So I'll go back to the first derivative test. So I'm going to say, well, around 0, I'm looking at negative 1 to 0. I'm looking at 0 to 1. And I have to look at what's going on. Is it increasing or decreasing? So now I'm going to go back to the first derivative and test a point. So first derivative at negative 0.5. Well, let's just think about this so I don't have to do too much work. 0.5, that's a positive squared is positive, so that's going to be a negative number. 0.5 squared is going to be less than 1, so minus 1, that's going to be a negative number. So this is going to be less than 0, so this is wrong. What did I do wrong here? No, this is positive, because that's always going to be positive. No, what did I... Oh, sorry. Okay, brain fart. Undo. A negative times a negative is not less than 0. It's greater than 0. So this is increasing between negative 1 and 0. If I look the same thing at a positive 0.5, if I check on this one, again, at a positive 0.5, this is even, so I'm going to get the same value whether I plug in a negative or a positive. Again, this will be a negative. This is going to be a negative number. Negative times a negative is positive. So this is positive. So this is not a relative extrema because it's increasing and it's increasing. First derivative test says it has to change from increasing to decreasing or decreasing to increasing. So this one has just two relative extremas. A relative max and a relative min. So that's the second derivative test. Lots of fun. What it comes down to with this section, it's pretty much doing the same thing as we've been doing the other ones. It just has that added pain of finding second derivatives. If your second derivative is easy to find, this is really easy to work with. If it's a pain to find, it's a pain to do it this way. But that's the second derivative test. That's where we're looking at concavity. We really wanted, if we want to look to see, what's the concavity? It kind of helps us sketch things in. What are we looking at for the graph? So let's go back to here and give you some homework to work on. Enjoy.